Hi everyone, in this video I'll be going over sections 5.3 and 5.4. Here we're seeing the connection between the two main pillars of Calc 1, the pillar of the derivative, and now we've been seeing a little bit of this integration side of things, and this fundamental theorem of calculus that we're seeing in 5.3 is really the connection between those two sides. So here's the theorem. It says if you have a function g of x that's equal to the integral of a function f of t over dt from a to x, here's a picture of it just to help out. I always like to kind of envision pictures when I'm looking at a potentially confusing theorem. So this is saying if you have a function f of t, so here's that function f of t, and then you integrate up to some value x from a to x, as long as that's within this interval a to b, here's a to b, then what you're getting out of this is a function for the area based on what x you choose, and that's why it is a function of x. So if I would have chosen an x back here, obviously we get a different amount of area, and that would be the associated area in that case. So this is exactly what's going on. It gives us a way of evaluating integrals without really the need of taking a Riemann sum. So if we use part 1, and this is just part 1 of the fundamental theorem, part 2 is really what is probably most important to us, and we'll see a lot of part 2 of this fundamental theorem. Part 1 is obviously important too because it connects the two sides of the derivative and integration. So let's say I want to find g prime of x, right? And that's what this connection is. It's a connection between an integral and a derivative. So what this says to do is to find the derivative of g, right? Here's g prime, here's g. So to differentiate when the function has been defined in terms of this integral, all you need to do is evaluate the inner function at the variable. It's that simple, actually. So we would have, instead of the square root of t plus t cubed, the derivative of this defined function would be the square root of x plus x cubed. Okay, that's it. So I'll go to part 5 over here, actually, on the next page. What if we're not just plugging in x, but what if we're plugging in x to the 4th? So what if we're going to x to the 4th rather than just x? How does that work? So y prime would be equal to cosine squared of x to the 4th. But just like the chain rule applies when we're taking derivatives in a different context, when we're taking derivatives of functions defined in terms of integrals, we still need the chain rule, actually. So I would need to multiply by d dx of x to the 4th to fully take this function's derivative. So I'd have y prime. Taking this derivative, I would have 4x cubed. I'll go ahead and write that out front. And then I would still have cosine squared of x to the 4th. This would be the full derivative, given this is our function. So as I was saying, there's two parts to the fundamental theorem, and the second part is really I don't want to say the more important part, but it's really the part that you emphasize going forward because it allows us to integrate so easily. In 5.2, we computed limits of Riemann sums. So we would allow this sum, its input, to approach infinity. And we would then be getting infinitely many rectangles and then therefore approaching the actual area under these curves. And that's kind of cool. It's a little annoying though when the functions are more complex. This part of the theorem allows us to very, very quickly integrate. So you might remember that we had been setting up a sum and a limit of that sum to evaluate the exact area under these things, or the exact value of these integrals. But what this is saying is if you can find an antiderivative, capital F of lowercase f, and evaluate that antiderivative at the upper limit, and then take away evaluating that antiderivative at the lower limit, that you are finding the exact area and the exact value of this integral. So this is a way of sidestepping the need for the Riemann sum and the limit of that Riemann sum. Kind of like when we went from the definition of the derivative to just taking power rule derivatives and chain rule derivatives and product rule and quotient rule derivatives. We didn't use the definition when we were just taking all those derivatives. That's kind of like what's happening here. That limit of a Riemann sum is essentially the definition of this definite integral. And now we're using the conclusion of that process. So what I need to do, here's my f of x. I need to find an antiderivative of this function. So I need to find a function over here so that if I were to take the derivative of that function, that this is the result. So what ends up happening is, in a polynomial situation such as this one, we do essentially the inverse of the power rule derivative. So instead of multiplying down and then lessening the power by 1, I'm going to increase the power by 1 and then divide by that new power. So this would be equal to, and here's the notation for this. So I'd have x cubed, right? Instead of x squared, I increase that by 1, then divide by that new power. This is the inverse of the power rule derivative. Plus, increase the power on the x by 1, so I'd have 3x squared now, over the new power. Minus 4x. The new power on x is 1. I would technically divide by that new power. And I would then have nothing more but to write this notation, which means this here. So I'll have to evaluate, this notation means I'm going to evaluate this antiderivative at 3, and then I'm going to subtract evaluating this antiderivative at 1. So basically performing this part. So I'll have 3 cubed over 3 plus 3 times 3 squared over 2 minus 4 times 3. That's evaluating the antiderivative at the upper limit, which is 3. And then I need to subtract parentheses so that I subtract the entirety of this second part, evaluating this antiderivative at 1. So I'll have 1 cubed over 3 plus 3 times 1 squared over 2 minus 4 times 1, and whatever this is will be my result. Okay, so 3 cubed over 3 plus 3 times 3 squared, and then I guess I need to divide by 2 I'm going to retype that. So 3 times 3 squared over 2 minus 4 times 3, and then minus parentheses. That'll just be a third, so I'll just type a third. This will be 3 halves. And then minus 4, end parentheses. So I get 38 thirds. Okay, so that would be the number for the area under the curve of this function from 1 to 3. FYI, if you have this type of calculator, this is one of those things I encourage you not to abuse this ability of your calculator, but just know that it's there. So right here, you have this button, and I think if actually I'm in complex mode, it won't work. So I'll press, yeah, so now I'm not in complex mode. So press this button, it looks like an integral. And what you can do is type this integral in, actually. So I'll need to reference x, since I have a variable x in the problem. So I'll have alpha, right parentheses to access x, and then square x plus 3 times alpha, right parentheses to access x, and then minus 4. Scroll up, put your upper limit and your lower limit, press equals. The calculator will think about it for a little bit, and then it will say, oh yeah, 38 thirds. So that's a thing. Let's go to part 4. Sorry about my cough. I'm not sick. All right, here's another one. So what you can sometimes do, it's sometimes hard to find an antiderivative of something that you're starting with. Like, I don't know exactly what the antiderivative of this would be. It's hard to know what function I take a derivative of to arrive at this. So you can do a little bit of algebra. So I'll separate this as 1 over root x plus x cubed over root x dx. Writing this more in terms of powers, if you remember, it was easier to take derivatives of things when they're written as powers. Similarly, I think it's easier to find antiderivatives of functions if they're written as powers rather than written as these kind of rational functions. So I'd have integral from 1 to 3 of x to the negative 1/2, right? 1 over root x, same as x to the negative 1/2. And then here, x cubed over root x, I'm basically taking a half away from 3. So this would be the same as plus x to the 5 halves, right? This is the same as 6 halves. Take one of those halves away and get 5 halves. And I wrote 5/5, but I meant 5 halves dx. Okay, so antiderivative now. So once you have this written this way, I think it's easier to find these antiderivatives if this is possible. So raise the power by 1, divide by that new power. So this would equal x to the 1/2, and then I'm dividing by that 1/2, right? Raise the power by 1, divide by that new power, plus raise the power by 1, I get x to the 7 halves over 7 halves. Divide by the new power. Evaluate this from 1 to 3. Not all limits are 1 to 3. I know the two I've done here in this video so far have been 1 to 3, but they're not always that way. I'll simplify this a little bit. This would be 2x to the 1/2 plus 2/7 x to the 7/2. And then evaluating that from 1 to 3. So fundamental theorem of calculus part 2 says I can take the upper minus the lower. So 2 times 3 to the 1/2 plus 2/7 times 3 to the 7/2 minus 2 times 1 to the 1/2 plus 2/7 times 1 to the 7/2. Okay, so maybe I'll be rounding this. Let's see. So I'll type this in: 2 times 3 raised to the 1/2 plus 2/7 times 3 raised to the 7/2 minus, oops, not minus yet. So minus parentheses, that'll just be a 2 plus 2/7. So yeah, it's giving me this kind of strange decimal. If this were a problem on a test, it'd probably say round to 3 decimals or 2 decimals or something. I'll just round to 2 decimals and say it's about 14.54. All right, moving on to page 105. Here's one where we're going to graph a bit, and then it looks like estimate the area, and then find the exact area. So it says for each, use a graph to find a rough estimate of the area of the region that lies beneath the given curve, then find the exact area. So what I'm going to do is graph root x from 0 to 16. So square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. And then square root of 16 is 4. Okay, so this is roughly the region that we're talking about. So it's this amount of area. So it doesn't really say like what number of rectangles to use. So I'll just go ahead and use right endpoints with, oh gosh, let's do 8 rectangles. So I'll do one right here. I'll do one right here, and so on. You could have chosen a different number of rectangles for sure. Doesn't really matter. If whatever number that you're choosing will be under infinity. So they all will be estimates. So this stuff looks like an overestimate, right? If your function is increasing in an interval, then right endpoints will be an overestimate in that interval. So let's see, I'll go ahead and say that area, so each width, the delta x in other words, would be 2. So I'll factor out that 2. And now I need to find the heights of all of these. So I would have the square root of 2, right? Because here's 2, I'm evaluating at 2. Plus the square root of 4, right here. Plus the square root of 6. I'm basically taking the square root of all these evens. Okay. Some of these simplify, some don't. So root 2 does not, but I can say 2 plus root 6 plus root 8. I can write 2 root 2. Root 10, I'll just leave that. Root 12, 2 root 3, plus root 14 plus 4. So 2 plus 4, 6. So I'll say 6. Root 2 plus 2 root 2, that's 3 root 2. So these are gone. These are gone. And then just this stuff. So plus root 6 plus root 10 plus 2 root 3 plus root 14. Okay, so here would be our estimate. Let's just see what that is. All right, so 2 times 6 plus 3 root 2 plus, oops, need to get out of that, root plus root 6 plus root 10. Nope, not looking good. Need to get out of there. Root plus root 10 plus 2 root 3 plus root 14. So here's our estimate, it looks like. Hopefully this is a good estimate. This is kind of a weird way to do it. You could have done it with fewer rectangles or more. So about 46.12. If I just take that to 2 decimals, and this would be square units. Okay, so now to find the exact. So if I want to know the exact area, this stuff kind of in dark blue, I need to integrate. So the exact area would be the integral from 0 to 16 of the square root of x dx. Okay, that would be the same as the integral from 0 to 16 of x to the 1/2 power dx. Raise the power by 1, divide by that new power. So I would have x 1/2 plus 1 would be now 3/2. Divide by 3/2. We're evaluating that from 0 to 16. So that would be the same as 2/3. Oops, sorry about that. 2/3 x to the 3/2, and then 0 to 16. So 2/3, 16, that's times 16 raised to the 3/2, and then minus 2/3 times 0 raised to the 3/2. So some quick arithmetic here. So here's a 0. So that whole thing is just 0. And now we have 2/3 of 16 to the 3/2. 16 to the 3/2 would be the same as, let me reduce that a bit. 2/3, the square root of 16 is 4, so this would be 4 cubed. 4 is the same as 2 squared, so 2/3 times 2 squared cubed over 1, technically. So here I have 2 to the 6th times 2 to the 1st, so I have a 2 to the 7th over 3. 2 to the 7th is 128. So it looks like 128 over 3. That's a 3 there. And that would be square units, and that would be the exact area under that curve. Just as a comparison, it's 42.6 forever, right? And our estimate was this 46.12. And we had the understanding that our estimate was an overestimate. So indeed, that 46.12 was an overestimate. This is the exact area here. Okay, so on to 5.4. This is integration formulas and the net change theorem. So you may need some integration formulas to complete the problems you're going to need to do still on 5.3. A bunch of those are here. So I'll let you all read through this. I'm going to kind of dive into one of these problems straight away. So example 1, find the general indefinite integral. So what we were doing previously was definite integration, where you have definite limits. So notice we do not have limits here. We're not going from 1 to 3 or anything to anything. This is undefined, it's indefinite, right? It's going on for an indefinite period of time. So all we're doing is looking for some antiderivative, just any one. So that way I can apply that wherever I care about on the x-axis. So what I want to do is look for the general antiderivative to this function, and then the general antiderivative to this piece of the function. So I'll have 7 times x raised to the 1/4 plus 1. So we'd get 5/4 divide by the new power. Okay, minus 3 times the antiderivative of cosecant squared. Luckily on the previous page, there's a formula. So interestingly, the area under the curve of cosecant depends on the negative cotangent. So that's kind of an interesting thing, but yeah, the antiderivative of cosecant squared is negative cotangent. So I would have here negative, sorry, that negative should go inside. I guess that'll be my c cotangent of x. Okay, so that's 3 times negative cotangent of x. And then I'm going to tack on an arbitrary constant. I'm not going to evaluate because there's just nowhere to evaluate this function. So just simplifying, invert and multiply, we get 28/5 x to the 5/4 plus 3 times cotangent of x plus c. So for these indefinite integrals, you always add an arbitrary constant, because if you think about now differentiating this, the question is, do you get this in here back, which is called the integrand. So the first fundamental theorem said if you take the derivative of this thing, then you should get back what is in your integrand, right? So because the derivative of a constant just disappears every time, we do get this. And this is the most general possible function that does that. Okay, let's do another one. So I'm skipping to page 109. So this says, for each of the following, evaluate the integral using a graphing utility, plot the integrand and make a rough sketch in your notes, and also note negative area regions and positive area regions on your sketch. Okay, so for part A, it says evaluate the integral. So from -2 to 3, we're integrating this parabola, x squared minus 3. So I need the antiderivative of this. So I'll have 1/3 x cubed minus 3x, and then I'll evaluate that from -2 to 3. So I'd have 1/3 times 3 cubed minus 3 times 3, and then subtract 1/3 -2 cubed minus 3 times -2. Right, we have to make sure that we're subtracting the entirety of this lower limit. So let's see, we get 27 over 3, we get 9 minus 9, actually, looks like there. And then minus, so this will be -8. So -8/3 plus 6. Go ahead and go to the calculator at that point just to help me out with that. So it looks like -10/3. Okay, so interesting. Let's draw a picture. So using a graphing utility, plot the integrand and make a rough sketch in your notes. So I'll just make the rough sketch. Feel free to pull up Desmos at this point. But for this parabola, this is a vertex down here at -3, 0, or sorry, 0, -3. And then I can go ahead and evaluate maybe at -2. So at -2, the function, I square -2 to get 4, subtract 3, I get a 1 at -2. So over here at -2, I'm at 1. So I have this piece of the parabola. And then evaluating at 3, the upper limit, sorry if that was hard to see. So 3, squaring 3, I get 9, minus 3, I get 6. So over here at 3, I'm up here at 6. So I have this other kind of parcel of the graph. All right, so what we're doing is we're looking for areas under the curve. So I'm kind of moving on to part C now. So this is part B / C here. So note negative area regions and positive area regions. So that's what part C is. Sorry, I was reading this. So what you're doing when you're integrating over these intervals like this is, if you imagine this little sliver, this chunk of area, and then this kind of sliver. So here you would have, let me write this, you would have positive area throughout this region. So when you're integrating from -2 to 3, the integral is going to count this chunk of area as positive. Same with this one. I can't write positive over there, but that's the same thing. So it's positive there as well. So there's a little sliver of positive, so that's adding to the positive side of the integral. But there's a large chunk of negative land, right? So all this stuff below the x-axis is actually counted as negative area, right? Remember that you're counting rectangles here still technically, and those rectangles in that region would have a negative height because the function values evaluated at those x's would produce those negative height rectangles. You're still going to have a positive width for every rectangle, but sometimes you have these negative height rectangles, right? So in other words, I'm saying all that to kind of explain why our answer is okay to be negative in certain cases, right? We're basically looking at some positive, right? Imagine I had $5, but then I go into debt by $20, right? So I'm coming out negative on that side of things. So if you only have negative region, for sure it'll all add up and be negative. In other cases, it's some positive adding to other negative, and the negative is kind of winning out here. Okay, so moving on. I'm going all the way to page 114, actually. So this is the Net Change Theorem. So this is a cool one. I think this is can be an aha moment. But basically this one's saying if you're integrating a rate of change function, this derivative function, then simply evaluating the original function, you're finding the kind of accumulation of that changing quantity. For instance, like imagine you're traveling and you're in your car driving up to LA and you want to know how far you went. If you have your rate of change function, what this is saying is you just need to actually integrate over that rate of change function, and what you arrive at is your distance. So if you're looking at some function like a velocity function, let's say you have a velocity function and it's like 10 meters per second. I don't know, something strange like that. When you integrate across a velocity function, all you're left with is the numerator that were defined in the units. So that kind of gives you insight into what you want to do often. So looking at example 3 here, it says the velocity of a particle in meters per second is given by this v of t, 3t minus 5 from 0 to 3. It says find the displacement, and it says find the distance traveled by the particle in the given time interval. So basically, to find the displacement, the change in the beginning and ending locations, we need to simply integrate from 0 to 3 this function. So for part A, this displacement, we would integrate 3t minus 5 dt from 0 to 3. Now what's going to happen is this thing is going to count some negative and some positive, just to give you a picture of what's going on. Right, from 0 to 3, you're going to look at something like this. So you would have a location of positive, and you would have, sorry, this would be negative, and then you would have a location of positive. So this is one where you're summing up both negative and positive. So you're finding just the difference in that. So that's why this gives a displacement rather than a distance. The distance is going to be wherever I have a negative interval, I need to take the absolute value of that region. So for displacement, I simply just integrate over the interval. So I'll have this equal to 3 times t squared all over 2 minus 5 times t, integrated from 0 to 3. And that, since they both depend on t, the 0 is not going to produce anything. I'll just have 3 halves times 3 squared minus 5 times 3. So I have 9 times 3, 27 over 2, minus 15. Let's see what that gives. Oops, sorry. Went off of the screen a lot today, sorry about that. So negative 3 halves. So it's actually, my picture is a little bit off. There's more area under the negative side. So we'd have negative 3 halves for that. Let me draw a better picture. That one wasn't great. So maybe over here. So this will be v of t, this will be t over here. So at 0, this thing is down at negative 5. And then at 3, this thing's over here at 4. So here's maybe 1, 2, 3. And 4, if this is negative 5, then maybe 4 is right about here. So this is our function. So we're looking at, this is 3. So we're looking at a region of positive. So this is that positive area. And then we're looking at a region of negative area. And integrating over that interval is telling us the difference in the beginning and starting positions of this function right? Integrating a velocity gives you a position function. Okay. Now for part B. So as we can see from our picture, from 0 to wherever this intersection is, right? And maybe we wonder where that is happening. From 0 to wherever that is happening, we get negative space. For the actual distance traveled by this thing, we don't care about the directionality anymore. So we want to take the absolute value of this section. So what we need to do is figure out where this is happening, right? So where is the velocity 0? So 3t minus 5 equals 0 at t equals 5/3 seconds. So what I need to do is integrate from 0 to 5/3 3t minus 5 dt. But then I need to take the absolute value of it, add that to the integral from 5/3, picking up the integral again, going from 5/3 to 3 this time, of 3t minus 5 dt. No integral needed, because this is our region where it's already positive anyways, right? So what I'll do is integrate and then evaluate within the absolute value here, and no need for the absolute value here, and that'll be the total distance regardless of what direction the object was moving. So we get 3t squared over 2 minus 5t evaluated from 0 to 5/3, but then absolute value of that, plus 3t squared over 2 minus 5t evaluated from 5/3 to 3. I'm going to grab a new sheet of paper so I can do the algebra on it. Okay, so here we are. We have absolute value of 3/2 5/3 squared minus 5 times 5/3 minus, this will be a 0 actually. When I evaluate at 0, right, we get a 0. So I just need to take the absolute value of this and then add this piece. So fundamental theorem part 2 says upper minus lower. Minus 3/2 times 5/3 squared minus 5, sorry about that, times 5/3, I believe. Okay, so we need to now type this into our calculator, and this will be the distance that the thing went, right? So what we did in part A is we figured out that the thing started at 0, and then at the end of its journey during 0 to 3, it was about a 1.5 meters behind where it started. So it's 1.5 meters, in other words, negative 1.5 meters behind where it started. What we're about to find here is after it did whatever journey it did, how far it traveled to end up negative 1.5 meters behind where it started. Okay. So absolute value, 3/2 times 5/3 squared minus 5 times 5/3. I'll go ahead and type minus 0 just because it's there. And then plus, outside of that absolute value, 3/2 times 3 squared minus 5 times 3. Then minus 3/2 times, anybody else having fun yet with this one? Squared minus 5 times 5/3. Can I not even type it? I think it's running out of memory. So 5 divided by 3. End parentheses. So 41/6. Okay. So this would be, the particle went 41/6 meters in total, which is equal to 6.83 meters. So, okay. Talk to you next time.